For the last, 70 years or so, one single material has been the absolute bedrock of our digital world: silicon. But that bedrock is starting to show some cracks. The incredible progress it fueled is slowing down, and a whole new race has begun to find out what's next. So let's dive into the materials that could completely redefine our future.
Just think about it for a second. The smartphone in your pocket, the car you drive, the cloud, everything is built on this promise of faster, smaller, more powerful electronics. But what happens when the very material that made all of that possible, silicon, starts hitting a wall? A physical wall it just can't get past. And this chart right here, this lays out the problem perfectly. That blue line, that's Moore's law, the steady, predictable doubling of computing power we all got used to every couple of years. But look at that red line. That's our demand, driven by things like AI and big data, and it's now doubling every 3.4 months. We're demanding a rocket ship, and our old silicon engine is just running out of fuel. Okay, so let's get into exactly why silicon, the undisputed champ for decades, is in so much trouble. It's had a fantastic run, but the laws of physics are finally catching up to our ambitions.
You see, the promise of Moore's law was really simple. Just shrink the transistors, pack more of them onto a chip, and boom, you get more power. But we literally can't shrink them anymore. They've gotten so small, they leak electricity, they guzzle way too much power, and they generate so much heat they risk melting themselves. So just making silicon smaller, that's not the answer anymore.
But here's the cool part. This challenge has sparked this huge wave of innovation. Scientists are exploring a whole new playbook of materials. So let's meet the main contenders in this thrilling race to go beyond silicon.
Okay, here's a quick look at the field. You've got the speed demons like graphene, then you have the power-handling workhorses gallium nitride and silicon carbide. There are these flexible specialists like organic semiconductors that can literally bend and fold. And then there are even wild cards like spintronics that completely rethink how computing works. Now, each one has incredible strengths, but also some pretty big hurdles to overcome.
So let's zoom in on our first head-to-head matchup. In the world of high-powered electronics, and I'm talking about stuff like electric vehicle chargers, massive data centers, the power grid itself, two materials are really battling it out: gallium nitride, or GaN, and silicon carbide, SiC.
Now, what's really interesting here is they aren't always direct rivals. You can think of GaN as the sprinter. Its electrons move incredibly fast, which makes it perfect for high-frequency stuff like 5G and advanced radar. It lets you build much smaller, more efficient power supplies. SiC, on the other hand, is the marathon runner. It's unbelievably tough and can handle extreme heat, making it perfect for the harshest industrial environment.
But in the applications where they do compete, well, the data's pretty clear. This chart tells the story. In a typical power converter, the GaN-based design has way less energy loss than both silicon and even SiC. A huge reason for this is that GaN has zero reverse recovery loss, which is basically a kind of energy waste that plagues other materials every single time they switch from on to off.
And here it is, the knockout punch: cost. This is the real game changer. You see, GaN devices can be grown right on top of standard cheap silicon wafers. They can piggyback on decades of manufacturing know-how. SiC, however, needs a much more complex and expensive process from the ground up. This chart shows GaN is on a clear path to being the cheapest of all three, which could drive absolutely massive adoption. Okay, but this whole race isn't just about being stronger or more efficient. The next group of materials we're going to look at can do things that silicon can only dream of. They open up entirely new possibilities for what electronics can even be. First up, graphene. It's a single atom-thick sheet of carbon, and it is a true wonder material. Seriously, it's stronger than steel, more conductive than copper, and almost perfectly see-through. The potential is enormous, but it has one major flaw for computing: it doesn't have a band gap. Think of it like a light switch that's just stuck in the on position. You can't easily turn it off, which is the most basic thing a transistor needs to do. And that brings us to a whole family of two-dimensional or 2D materials. Okay, look here. On the left, that's a traditional silicon transistor. The electrons flow through a pretty thick channel. But on the right, that's a 2D transistor. Because the material is atomically thin, you can control the flow of electrons with incredible precision, using gates on both the top and the bottom. This opens up a whole new dimension of control, which means smaller, faster, and way more efficient transistors.
So what does that new dimension of control actually get you? Well, let's take a common logic gate called an XNOR, a fundamental building block of any computer. To build one using today's silicon technology, you need to wire together 12 separate transistors. Okay? Remember that number 12.
With a 2D material, using those top and bottom gates, you can perform that same exact function with a single transistor. 12 versus 1. This isn't just a small improvement, this is a revolutionary leap in how much computing we can pack into a tiny space.
Now, let's talk about changing the very shape of electronics. Organic, carbon-based semiconductors, they aren't as fast as silicon, but they have a superpower. They're flexible. This is the tech that's going to give us rollable TVs, wearable medical sensors that are actually woven into your clothes, and maybe even electronics that can be integrated right onto your skin. The big challenge right now is just making them last as long and work as well as their rigid cousins.
Okay, let's get even more futuristic with a concept called spintronics. You see, all modern electronics work by pushing an electron's charge around, but electrons have another property called spin, which is kind of like a tiny internal magnet. Spintronics wants to use the direction of that magnet, call it north or south, to represent data. And the payoff? We're talking about potentially instant-on computers with memory that doesn't forget anything when you turn the power on.
And now for the holy grail of efficiency. Researchers are looking at topological materials. These are exotic materials where electricity can flow along these protected superhighways on the edges without any resistance or energy loss at all. A theoretical topological transistor could smash a fundamental energy limit of today's chips, known as Boltzmann's tyranny, which is basically an energy tax that every single transistor has to pay just to switch on. These new ones could operate almost tax-free.
So we've seen all these incredible contenders. We've got GaN, we've got 2D materials, organics. So who's going to win the race? Who's going to be the one to replace silicon? Well, the answer might actually surprise you.
Here's the most important takeaway of all. There is no single winner. The future isn't about one material taking over. It's about a whole conversation happening between many materials. Silicon will probably stay the foundation, but it's going to be supported by a whole team of specialists. GaN for handling efficient power, 2D materials for doing dense logic, and organic semiconductors for creating entirely new flexible forms. As the researchers behind one of our sources put it, we are standing on the brink of a new era. The end of silicon's complete dominance isn't an ending at all. It's the beginning of a much richer, more diverse, and frankly, more powerful technological age.
The silicon chip gave us the information age. It put a computer in every pocket and connected the entire globe. So the question we're left with is this: what new reality, what new age will this incredible family of materials build for us next?